Welcome back, students. Up to this point in class, we have done a lot of work and calculations specifically on ideal gases. In the last lecture, we investigated the properties of real gases and talked about how they differed from ideal gases. Substances are not all ideal gases, and many substances, we're familiar, are actually solids or liquids. These states of matter are very dense and have very different properties than gases, meaning we need different tools to describe them. In this section, we will investigate phase changes where matter goes between solid, liquid, and gases. The learning goals for today are going to be to determine the most stable phase using chemical potentials. So we're all familiar with the idea that different substances are stable in different phases, but here we're going to look at why. And then we're going to spend the most of the time in this lecture focusing on PT diagrams, which are relationships between the pressure and temperature. We'll also bring the volume in towards the end and see how all of these variables relate to each other and help explain the phase that matter will be in. So, like I mentioned, everyone is familiar with the fact that some substances are naturally solids, while some are liquids and some are gases. What we want to do here is move beyond that fact of knowing this and ask, well, why are some substances liquids, solids, and gases? Why is water a liquid while methane is a gas at room temperature? Ultimately, it does rely on the intermolecular forces between these atoms, but we can describe this using the Gibbs free energy. We know that the Gibbs free energy is always negative. The change in Gibbs free energy is negative for a spontaneous process. So if we have two different states of matter, the one with the lowest Gibbs free energy will be favored because it would give a negative change in Gibbs free energy for any other substance to transition into that substance. And this is dependent on pressure and temperature. So we'll start with temperature and then we'll consider pressure. What we have here is if we want to know how the Gibbs free energy is changing, and like we saw earlier, we're going to mostly focus on this idea of chemical potential, which remember is just the molar Gibbs free energy. So the molar Gibbs free energy change then is simply equal to the derivative of the molar Gibbs free energy with respect to temperature at constant pressure times the extent of the temperature change, and then the derivative of the Gibbs free energy with respect to pressure at constant temperature times the extent of pressure change. And using our Maxwell relations, we can plug in for these terms. We know that dg dt is negative S. Since we have a molar Gibbs free energy, we now have a molar entropy. And then if we have the dg dp, that is the molar volume. So our chemical potential for substances will change based on temperature to the tune of the molar entropy, and by pressure to the tune of the molar volume. So like I said, we'll start with temperature. As we increase the temperature, we can see that the chemical potential will decrease by the molar entropy. How does the molar entropy change with temperature? It does to the tune of the natural log of temperature, but it's approximately constant. So for this kind of back of the envelope calculation that we'll be doing, we can simply assume that the molar entropy is a line. So we have linear molar entropies, but how do they change by the states of matter? And we should be pretty familiar with this. So solid phases are very dense and very organized, so they have very low entropies. Liquid phases are also pretty dense and organized, but slightly less dense and organized than solid, so they have an increase in their molar entropy, while gases are very expansive and very disorganized, so they have a very large molar entropy. So we have these differences in molar entropies here. Why is it important that these molar entropies differ? Well, consider what they would be. Remember that the rate of the chemical potential change with respect to temperature is approximately the molar entropy of these phases, and these are approximately constant. So what do they look like? Well, for the solid, we would have a negative curve because we have the negative molar entropy that decreases in an approximately linear fashion as temperature increases. Now for the liquid, it's the same, but the liquid has more entropy, so the slope is steeper, and the gas has even more entropy, so the slope is even steeper. Putting these three things together, if we have three lines with three different slopes, they are bound to intersect at some point. And these intersections are the melting temperature and the boiling temperature. So for temperatures below the melting temperature, the solid phase has the lowest chemical potential, meaning the solid phase is favored over the liquid or the gas phases. Once we increase past the melting temperature, but not yet to the boiling temperature, the liquid has the lowest chemical potential, meaning the liquid is favored. Once we increase above the boiling temperature, the gas has the lowest chemical potential and the gas is favored. We can have some situations where we are outside of equilibrium and we can have super cooled or superheated liquids or solids where we are regions that are above this. So for example, something that I routinely did in grad school is have antibiotic in the freezer. And for some reason, based on the small volume we had, it wouldn't freeze. So it would be up in this region. If you whacked it on the desk, it would instantly freeze and all crystallize. And that was pretty fun. Now that's fun, but having it the other direction is pretty dangerous because of having a superheated liquid that all of a sudden transitions to gas that leads to explosions and massive increases in pressure and so forth. We can also think about the packing here, and depending on the time we have, we might talk a little bit about liquid crystals, but essentially you can have solids, and we talked about this earlier. Solids are very well organized, liquids are not so well organized, and gases are totally disorganized. Liquid crystals represent something that kind of looks like a solid, but doesn't quite have the perfect packing that a solid crystal needs. Like we mentioned earlier, the phases of matter is also a function of pressure, not just temperature. So we'll start by considering carbon dioxide, and you likely all are aware that carbon dioxide is dry ice. And it's called dry ice because it looks like an ice cube, but then it doesn't melt. It goes right to the gas phase. That's because at atmospheric pressures, the gas line intersects the solid line before the liquid. So that means there is no point at atmospheric pressure where the liquid phase is more stable than either the solid or the gas phase. So this substance sublimes rather than go through a melting and then boiling point. This is only true at atmospheric pressure. We can change the pressure of carbon dioxide, and we can in fact make liquid carbon dioxide exist. There'll be a link to the video later in the lecture, and I won't play it during the recording, but we'll watch it in class, that goes through reaching the critical temperature and pressure of carbon dioxide, since it's at pretty reachable pressures and temperatures. We saw on the last slide that the chemical potential with respect to pressure changes by the molar volume. The molar volume is a positive number, so this leads to an increase in all of these curves. We have two different scenarios based on the substance that we're exploring. So we can see that all of these increase, and in most cases, the volume of a solid is smaller than the liquid, which is smaller than the gas. For some substances, most notably water, the liquid actually has the smallest volume. So the smaller the molar volume, the smaller the shift. So since gases have a large molar volume, they are shifted much more than either the solids or the liquids. And it's important to note that for this cartoon here, the liquid and solid shifting is exaggerated compared to the gas. It's usually much, much less than the gas. So what happens, and why do we care that they're shifting based on molar volume? The solid lines represent the normal pressure, and the dashed lines represent the new pressure, where we have increased chemical potential based on molar volume. And what you can see is that there is a shift in the points where these intersect. So looking at the gas is shifted up a lot, the liquid is shifted up a little bit, and instead of intersecting down here at the normal boiling point, they now intersect up here. And this leads to a boiling point elevation. So increasing the pressure on a liquid always increases the boiling point. And this is always true for every substance. And you probably heard things like if people live in Denver, they have to boil their noodles for longer because the pressure is less up there. So the boiling point is lower, so they're not cooking it at hot of a temperature. And that's true. That's the opposite effect of what we're talking about here. So if someone lived maybe at the very deep pit or something rather than on a very high mountain, they would have to boil their macaroni and cheese for less time in order to get it to cook, because water would boil maybe at 103 degrees Celsius or something like that. Looking at the normal substances, we see a similar thing for liquids. So since the solid shifts and the liquid shifts more than the solid, that also leads to a melting point elevation. Now, for other substances like water, where the liquid shifts less than the solid, they actually intersect at a lower temperature, and you can get a freezing point depression for these substances. And so we'll always look at normal substances, and then we'll always throw water in there as well, because water is probably the most normal substance we can think of, even though its phase change is different than everything else. Here we'll look at what's called a PT diagram, and this is simply a plot of pressure and temperature, and then in the shaded regions here are the different phases of matter that can exist. Most points on this PT diagram consist of a single phase of matter. So you can see the gas here is existing at very low pressures and very high temperatures. The solid is existing at low pressures and high temperatures, and the liquid is in between them. At this point, so if I were at a point right about here, I would only be in the gas phase. Here I would be in the solid phase, here in the liquid phase. These points are separated by boundaries, and these are called coexistence curves. So at any of these points along this coexistence curve, I would have solid and gas present in my sample. Here I would have liquid and gas, and here I would have solid and liquid. These three curves are different. We'll see what they are in the next lecture. I've got a mathematical framework for them. They all intersect at the triple point. This is a point where all three phases of matter are capable of existing at the same time. This is unique for every substance. So for water, the triple point happens very near 0 degrees Celsius, and it's a pretty low pressure, somewhere about like 0.01 bar or something like that. So in theory, if you put ice water in a vacuum and pull the strong enough vacuum, you should be able to boil that ice water. As we increase, so if we look here, the slope of this line from solid to gas is always positive, and the slope between liquid to gas is always positive. And this reflects the fact that gas is less dense than solid or liquid. In most cases, the liquid is less dense than the solid, leading to a positive line. Again, this is exaggerated here. It's in general almost vertical, no matter what the substance is. And if we have these weird substances like water, where the liquid is more dense than the solid, we would actually have a negative sloping line here. So you can follow along this curve in anywhere you want, and that's going to give you the phase changes that occur. So if we start at one pressure, like normal atmospheric pressure, if we started with a solid, as we increase the temperature, that solid would melt. And then if we keep increasing the temperature, that liquid would boil. If we did it at a very low pressure, instead of seeing boiling, we would see sublimation as it crosses the below the triple point. There's no liquid phase. We could also imagine what will happen if we just increase the pressure. So if we increase the pressure, the least dense state of matter will be favored. And so as we increase the pressure on a gas, it would go to the liquid and then the solid. If this were one of those weird substances like water, it would actually go from solid to liquid. And we'll see an example of this in class. We'll melt some ice with pressure. What happens at these phase change boundaries? You're probably familiar with this, but of course we have to add heat to get the phase to change. So you can imagine boiling water. The slowest part of boiling water is increasing the temperature of water from 100 to 101 degrees. It takes a lot of energy to boil and remove that water and get it out of the gas phase. It's actually pretty easy to get it from, say, room temperature to 99 or 100 degrees, but the boiling takes a lot of heat. And this heat is calculated at constant pressure, because when you're boiling something, the pressure is unchanging. And so what we have is an enthalpy. So this plot here talks about the amount of heat that's needed to increase the temperature. So as heat is added to the solid, the temperature of the solid increases until we get to the melting point, where now the heat, instead of going to increasing the temperature, goes to melting the substance and turning it into a liquid. And the enthalpy of this, the heat of this process, is known as the enthalpy of fusion. We also have the enthalpy of vaporization, where the transition is happening between liquid and gas. And if we wanted to know how much heat was added, we would have to integrate under this whole curve here. So it turns out that the enthalpy for fusion and vaporization, the heat involved is pretty constant as a function of pressure and temperature. If we wanted to talk about sublimation, we could do that as well. And there's an enthalpy of sublimation. It turns out that for the most part, the enthalpy of sublimation is simply equal to the sum of the enthalpy of fusion and vaporization. Now, why is that the case? Well, imagine a pathway where you went to A and then went all the way to the end here. And now what if you started at B, went all the way to the end, and then increased the pressure? Well, if you did that, you would have a state function. So if you went from A across here, or if you went from A to B to here, you would start at the same point, end at the same point. So the heat or the enthalpy of that process would need to be the same. And so the temperature change is pretty similar, but what's happening here is you're having melting and boiling, which is then going to be the same as sublimation. So the sublimation enthalpies are often not listed, but if you need to calculate them, they're simply the sum of the fusion and vaporization enthalpies. Here we're looking at a more realistic phase diagram. So the last one was kind of arbitrary. Here we're looking at the phase diagram for carbon dioxide. And you can see at a normal atmospheric pressure, we sublime the carbon dioxide rather than melting it. And there's a sublimation point. So in order to get dry ice, you have to cool it down below 78.5 degrees C. And above that, it will sublime and be more stable in the gas phase. If we increase it to about 5 atmospheres, we can hit the triple point, and above that, we can get more liquid state available. I'll mention the critical point here. This critical point, we talked about it in the last chapter, is an interesting point. It's the point by which we can't distinguish the liquid and the gas any further. So above the critical point, there's no fine distinction between liquid and gas, where the densities of these become the same. And we'll watch a little YouTube video in class that goes into this and shows what it looks like as you actually cross this critical point. And it'll be done for carbon dioxide, because as you can see, this critical point is happening around, say, 10 or 20 atmospheres, which isn't too high, and at temperatures of about 35 degrees Celsius, which is not high at all. So you can actually pretty easily hit the triple point or the critical point of carbon dioxide. Many substances have more than one solid state. So we'll look at this for water. Here is a phase diagram for water with an exaggerated line here. You can see what would happen as we increase the pressure on gaseous water is at some point we would cross this line and be more stable in the liquid phase. To look at a more realistic diagram, we can pull this one up from the book, and this shows us a whole bunch of states of water. And so this is the normal curve that we were looking at. You can see that this line is almost vertical here as the pressure increases. The pressure is increasing quite drastically here on the y-axis. And we don't only have one solid phase shown here, but we have many solid phases. And so I think the highest number is 11. There's up to 11 different solid phases for ice. These solid phases differ in the crystal packing. And you can always note which phase is denser by looking at which one is favored at high pressure. So if we look, we have liquid water is favored over normal ice because it is favored at high pressure. But these sorts of ice, so like ice 5, ice 6, ice 7, ice 10, these are all more dense than liquid water. So this is an example of normal ice. This is ice 1 that's stable under atmospheric conditions. This is a rhombic form. This is ice 6 here that's stable under pressures of about a gigapascal, which is pretty high. And this is more densely packed than water. So if we had a coexistence of liquid water and ice 6 at this coexistence curve, this ice would actually sink in the liquid water. We can note something else here, and we'll see this on the next slide. This is called the phase rule. At no point on this plot does there exist more than 3 phases simultaneously. So we have the normal triple point here of solid, liquid, and gas, and we have some other triple points. So we have a triple point here of ice 6, ice 7, and liquid water. We have a triple point here of ice 8, ice 7, and ice 6. We have 8, 7, and 10. We have ice 9, 11, and 1. So we have triple points, and we have coexistence curves, but we never have triple curves or quadruple points. These don't exist. And this was formulated as the phase rule by Josiah Willard Gibbs himself. The phase rule states that the number of degrees of freedom a state has is 3 minus the number of phases. So we can consider first one phase. So if we had one phase here, we're sitting in the gas phase only, you could change the pressure without changing the phase, and you can change the temperature without changing the phase. There are 2 degrees of freedom, pressure and temperature. However, if you have 2 phases, like we've shown here, an alpha and a beta phase, which could be solid and liquid, liquid and gas, whatever it could be, you only have 1 degree of freedom, meaning if I'm sitting at this coexistence curve where liquid and gas are present, and I want to change the system in some way, maybe I want to change the temperature, but keep having liquid and gas, the pressure also changes as a function of this coexistence curve. So I'm not free to change either the temperature or the pressure, but I must change them together if I wanted to change the system. If I have a third phase, I have 0 degrees of freedom. So I can have 3 phases of matter all coexisting at the triple point, but I can't change anything about that triple point. I can't change the pressure or the temperature without destroying one of those phases of matter. And this is the phase rule. Essentially, it allows us to figure out what these sorts of things would look like and tell if something is not real. So we'll never see triple curves on a PT diagram, and we'll never see quadruple points on a PT diagram. Those are not possible to exist. Now, what we'll note is that we could also see these if we looked at a different kind of diagram. So what we'll do here is look at, rather than a PT diagram, we'll look at a PV diagram. And now we do see everything I just mentioned. So we extend all of the dimensions by 1 degree. So instead of having a triple point, we have a triple line. And instead of having a liquid and gas coexistence curve and solid and liquid curves and solid and gas curves, we have these areas. Now, why do we have areas rather than lines or points, and lines rather than points? It's because of the nature of what the volume means. So there's only one temperature and pressure at which a substance can exist at the triple point. And we can only have one temperature and pressure where we have all solids, liquids, and gases. But the volume is a little bit different. So imagine I have a substance and I have mostly solid, maybe I have water with 1 ice cube in it and a couple of bubbles of water vapor. The volume of that is going to be pretty low. Now, as I increase the volume, I can keep the pressure and temperature the same, so I'm still at the triple point, but I can convert that solid and liquid into mostly gas. And so mostly gas will have a much higher volume than mostly solid and liquid. So all of these points here exist where I can have solid and liquid and gas all together. Here I'll have mostly solid and liquid. Here I'll have mostly gas. And the same is true for the other normal changes. So here my curve becomes an area because I can change the volume a little bit as I convert from solid to gas or solid to liquid. I can also put this together along with a PT diagram to get a PVT diagram. And you can see here, this is a complex, 3-dimensional shape, but this really accurately represents what's happening as you change the pressure. We're going to follow this A through F line here. Hopefully you can see that the pressure isn't changing for this line. And what we're looking at is how the volume and temperature change as a function of heating, essentially. So at the beginning, at point A, we're at very low temperature. And as we add heat, we increase the temperature, and the volume stays approximately constant as the solid is heated. Then once we get to this solid-liquid conversion, the temperature now stays constant. As the volume increases, the substance melts. Then we go and continue to heat. So as heat is continued to be added, the volume doesn't change. As we melt, or as we increase the temperature of the liquid, then we hit this liquid gas curve, and now we melt. So instead of increasing the temperature, we now increase the volume. And then once we get past this point, it's a little bit hard to see, but we'll increase both in volume and temperature as the gas is heated. And so you can follow along some of these other points as well if you want to understand what's happening to a substance as we change its phase. Now, this is in general an arbitrary sort of volume here. You can construct one of these for any substance that you want. These PVT diagrams are often a little bit too crowded to get more information out of, even though they do provide more information than either the PV or PT diagrams. And it's often enough to look at a PT diagram. So we'll focus on that for the remainder of those lectures here. In the next lecture, we will continue to investigate the phase changes that substances undergo and develop a mathematical framework to describe the PT diagrams.